The measure of intelligence is the ability to change. Hi all, welcome back. Dr. Clark here, and we are going to continue discussing chemistry. And so last time we discussed just basic chemistry, basic chemical properties like what atoms are made out of, protons, neutrons, electrons, that kind of thing. Now we're going to talk about, well, what occurs when you combine atoms that would make a molecule. And we're going to talk about properties of one of the most important molecules, that is water. So here you can see some stages of water. You can see water in the solid form or ice. And you can see the spaces in between the molecules. That's very important. That allows for the density of this solid to be less than the density of the liquid. You can see that the liquid molecules are more tightly packed together. They're randomly spaced and they're higher in density, especially at 4 degrees Celsius. Okay, so that's one of the neat and unique properties of water is that ice floats. All right, so you can also see here water binding with other water molecules and they're forming hydrogen bonds. Hydrogen bonds are very important when it comes to dissolving material, when it comes to functionality like the bonds that you find in DNA. A lot of this is based on hydrogen bonds. Hydrogen bonds are weak bonds. We'll come back to this in a second. Okay, they're weak bonds, but collectively, when you got lots of them, because you can have a lot of hydrogen bonds, you know that once these items bond up and they form ice, that ice can be very, very strong. Okay, so we're going to come full circle and talk more about water as we progress through the lecture. Okay, so molecules, like I said before, are just groups of atoms that are held together by energy. That holding together is what we call bonds. So holding two atoms together via energy is called a chemical bond. Now there are a few different types of chemical bonds that we're going to discuss in this course. The three bonds that we're going to discuss in this course are ionic, covalent, and hydrogen bonds. We're going to cover each one of these in a little bit more detail. First, let's talk about ionic bonds. So you might have saw that in that water molecule, you might have saw that one side of the molecule has a positive charge and the other side has a negative charge. Technically, this is an ionic bond. However, in the case of water molecules, because it's utilizing hydrogen, it is a hydrogen bond. We'll come back to that. Okay? But ionic bonds are the attraction of atoms to one another because of electric charge, because they have the opposite electric charge. When these molecules are formed, majority of the time they make crystals, or their stable solid structure is a crystalline form. So for example, table salt or NaCl, sodium chloride, is a sodium atom and a chlorine atom. Now, the chlorine atom has a negative charge and the sodium atom has a positive charge. You can see that this sodium atom is going to lose an electron to the chloride atom. In doing so, they're going to bond together. That means chloride has more electrons than it once had, which will give it a negative charge. And sodium will have less electrons than it once had, which will give it a positive charge. But together, they're going to have a neutral charge, and they're going to form a crystal form. Okay. So, this process, this bonding process, is really about a positive binding to a negative. Covalent bonds, on the other hand, are the strongest bonds. And these bonds are about sharing of electrons. So you're not losing an electron to another atom. Instead, the molecules will share time with that electron. That doesn't mean the sharing is equal. So at times, the electron will spend more time next to the nucleus of one atom than the other atom. If that's the case, often you'll have what we call a polar molecule. So the molecule will have a charge on one side and a different charge on the other side. Now, how many electrons are shared will depend on how many free orbitals that molecule has. They're trying to fill their outermost electron shell. So if they only need one electron, then they would just share one electron to fill that outermost shell. If you're a molecule, or if you're an element like carbon, and you need 4 electrons to fill your outermost shell, then you're going to bind to things and share 4 electrons so you can be a more stable molecule. Now, like I said before, covalent bonds are the strongest bonds that we're going to talk about. So, when we talk about covalent bonds, when it's bond for bond, covalent bonds are the strongest. Often, hydrogen bonds are stronger than covalently bonded molecules because hydrogen bonded molecules can have more bonds. And I'll show you what I'm talking about in a second. So here's some examples of covalent bonds. So you have things like 2 hydrogen. They each have an electron, so they can share an electron. So their outermost shell needs 2 electrons to be complete. So they can share these electrons between each other. And hydrogen gas is formed, and that's a stable molecule. You can see here carbon, like I said before, it needs 4 electrons. So it can bind up to 4 hydrogens, sharing an electron from each one of those hydrogens, single bond to each one of those hydrogen, and this makes methane gas. And then you can see oxygen here. Oxygen needs 2 electrons to fill its outermost shell. So oxygen can bind to itself, share 2 electrons between the 2 nucleus. On each side it is sharing 2 electrons. Okay. So now the outermost shell is complete, the molecule is stable, and you form oxygen gas. Now you can see here, this is a single electron. These are single electron sharing, but here, because they're sharing 2 electrons, we represent that as a double bond or a double covalent bond. Let's say they were sharing 3 electrons. Then it would be a triple covalent bond or a triple bond. Now, like I stated, at the beginning, that not all covalent bonds are equal. Some covalent bonds are what we call polar, and that's when one nucleus, remember, one center of the atom, the nucleus of the atom, that comprised of protons and neutrons, one of them attracts shared electrons more. Right? So it's pulling the electron closer to their nucleus. So one side of the molecule is going to have a negative charge. The other side of the molecule will have a positive charge. That attraction is what we call electronegativity or electron negativity. Different atoms have different levels of electron negativity. So they share electrons, with other things different. For example, oxygen has a higher electronegativity than hydrogen. So when oxygen and hydrogen bond together, oxygen pulls the electrons closer to its nucleus than hydrogen atoms. So the hydrogen atoms are basically losing the electrons to oxygen. Now it's not complete. It's not like an ionic bond where the electron is removed and goes to the electron shell of an atom. It's just pulling it closer. So this is how you get that a different charge on one side of the molecule compared to the other side of the molecule. So that unequal sharing results in polar molecules. This is very, very important because polar molecules will have different chemical properties and chemical behaviors. So some polar molecules, they are going to, most polar molecules are going to readily react with water because water is a polar molecule. Right, so they're readily going to react in water and dissolve in water. Now, non-polar molecules, things that are, share electrons equally between the two nuclei, they're often non-polar, and they will not react in water. They will not dissolve in water. And we'll come back to those kind of properties. It's important for what progresses or what can dissolve in water, what can move into cells, what kind of medicine can you make. These kind of things will be determined on, what are the properties of that molecule and how can that molecule be taken up with or by an organism that takes in things in liquid or, a water-based form. All right, hydrogen bonds. Hydrogen bonds are a lot like covalent bonds in the sense that it's dealing with positive and negative, but the electrons are not removed. And they're a lot like covalent bonds where electrons are not being shared equally, but they are involving hydrogen. And hydrogen, which is going to have, it's going to be an ion, it's going to have a positive charge, it is going to react or bind to the negative side of a molecule, the negative end of a molecule. You can think of it just like a magnet in the sense that you're going to get a positive side of one molecule reacting with the negative side of another molecule. And you'll know, if you remember magnets, they have a positive and a negative side. If you flip it positive, positive, and try to stick the two together, it's not going to work. You flip it over and negative, positive, then it works. That's also how hydrogen bonds are going to form in solution. All right, so if you're trying to dissolve something in water, which is going to readily form hydrogen bonds with that, if there's a positive and negative side to that molecule, they will arrange themselves so the negative and positive come together and the material will dissolve in water. Let's say that there's no positive and negative side to that molecule. It doesn't have a charge whatsoever. When it interacts with water, there's no interaction. it can't be dissolved because that molecule is nonpolar. There's no charge to that molecule. So it just sits there and they do not combine. Right? You might be thinking, well, what doesn't combine in water? Well, fat, oil. Okay? That oil will sit right on top of the water. Well, that's because that oil does not have a charge. It's a nonpolar molecule. Okay? So that oil is a nonpolar molecule and won't bind and won't have a hydrogen bond between things. Okay? We'll come back and we'll look at some more examples of these in lab and also further in lecture. Now, like I said before, covalent bonds are the strongest bonds, just one for one. If you're comparing a single covalent bond to a single ionic bond or to a single hydrogen bond, covalent bonds are the strongest. Okay. But when you talk about the strength of bonds, plural, hydrogen bonds are very strong in many situations because hydrogen only has one proton and one electron. It can form hydrogen bonds basically with anything that needs that electron. Okay? On top of that, because we're talking about this polar side and positive side and negative side, those hydrogen bonds will often form and stabilize the molecule as a whole versus creating a positive and negative side, which often will happen in covalent bonds. That's where the original positive and negative sides will come out. You'll see what I'm talking about when we start talking more about properties of water and hydrogen bonds and where they form. All right, so here you can see water molecules just like the water molecules that I was showing at the very beginning. Okay? They are forming hydrogen bonds with each other. So the positive side is on the hydrogen side. The molecule is positive over here. The negative is on the oxygen side. I told you that oxygen has a higher electronegativity, so it pulls the electron towards its nucleus, creating a negative side over here and a positive side over here. So the formation of water is a covalent bond. The formation of a water molecule is a polar covalent bond. But the bonds that water can form are hydrogen bonds. Right? Because the positive hydrogen, is binding to the negative oxygen in this case. Okay? Here you can see you got a similar situation down here. You have this long carbon chain. This is an organic molecule. Anything that has a carbon backbone is called an organic molecule. So this has got a carbon backbone or carbon chain. These are covalent bonds. Then you get this covalent bond that's bonding to oxygen. Oxygen's binding to hydrogen. That forms a covalent bond. So all these are covalent bond. But here, this hydrogen is going to have a charge. It's going to be positive. So this is a polar molecule because of this, what's called a hydroxyl group, this OH group at the end. Okay? That has a positive charge. This is a water molecule. Also, these bonds here are covalent bonds. Okay? But this oxygen, because it's a polar molecule, has a negative charge. And then they can form a hydrogen bond. This hydrogen to oxygen based on charge. Okay? Not based on the sharing of electrons, but this is based on the charge between the two molecules. Okay? I hope that clears up the differences between the types of bonds. So let's talk about what properties are unique to hydrogen bonds or because of hydrogen bonds. We know this, and we've known this for a very long time, since we basically started studying life on this planet. All life has to involve water in some way. Okay? So without water, we don't have life on our planet. This is why when we search for life on other planets, we're always searching for water first. If we can find water, then there's the potential for life, at least as we know life, okay, on our planet, because all life on our planet has to involve water. Okay? So that's why we're searching for water on other planets. It's not to say that there isn't the possibility that there's life out there that doesn't need water. That's possible. But based on what we know about life, it needs water. So water is essential to life. We know that we have a lot of chemistry, a lot of chemists at different institutions worldwide that study the properties of water. Because it's so essential for life, we need to ensure that we can, for lack of a better term, make sure that all the water on this planet is utilized and can be utilized to its best capabilities. So in other words, all the water that's on our planet right now is all the water that's been on our planet for 4.6 billion years. Right? Every single water molecule, it's just a giant cycle. So when the dinosaurs were drinking fresh water and urinating that water out, and it's taken up in the plants and transpired back in the atmosphere and rains down, etc. Right? The water that you're drinking in your water bottle could have definitely and probably most definitely ran through the kidneys of a dinosaur. So yes, you're drinking dinosaur pee. Okay? But not just dinosaur pee, bird pee, okay, bat pee, elephants, whatever. You name the organism, it's been through them in their lifetime, and in your lifetime, it will go into other organisms. Because every single drop of water that occurs on the planet today occurred on the planet when dinosaurs were roaming the planet, occurred on the planet when there was no such thing as life on the planet, everything. So from that perspective, there are a lot of chemists out there that are examining the water and the water sources that we have and trying to eliminate the pollution from the water sources, or trying to utilize water as an energy source, okay, by breaking water bonds, okay, using the energy from breaking those water bonds to drive work, and then eventually that water would just reform. So we'll come back to that when we talk about some of the unique ideas around renewable resources. As kind of one of the key issues, current issues in biology, is using renewable resources, whether that be solar, wind, whether that be using hydro, nuclear. Is it possible that we can get other renewable resources like water and utilize them as an energy source? And so there are a lot of chemists and physicists and engineers and biologists that are examining water properties for that purpose. Okay, we talked about this before. Water's a polar molecule. Because it's a polar molecule, it can form hydrogen bonds. It can form hydrogen bonds with itself, okay, which gives us these unique specific properties. Okay, first of all, water has excellent heat storage. So when we talk about the photons that our planet is absorbing from the sun, okay, the free energy from the sun, Our planet regulates and maintains its temperature very well because about 70% of our planet is water. Okay? That temperature sink, or that temperature capability, that storage capability, keeps our planet and maintains our temperatures on our planet to kind of a relative range. If you look at other planets that don't have water, they can heat up really fast, and then when the sun is not, beating down on that side of the planet, it cools down to extremes. So it will go from basically boiling to freezing in one day, every single day. Boiling to freezing, boiling to freezing. Our planet doesn't do that because of the storage sink that we get from our oceans and our rivers and streams and our glaciers, etc. So water holds temperature well, and it's slow to change. Doesn't mean it won't change, doesn't mean it doesn't change. I mean, we know that we have seasons, okay, but it takes a longer period of time for that change to occur. It's not a daily boiling to freezing change. Probably the most important feature or specific feature of water is the density feature. Okay? That ice is less dense than liquid water, right? Especially at 4 degrees Celsius. Liquid water at 4 degrees Celsius is the most dense. Okay? And so if you go to a lake and the lake is deep and you drop a thermometer to the bottom of that lake, the temperature at the bottom of that lake is going to be 4 degrees Celsius, because that is the point that water is most dense. Most dense meaning the heaviest. Okay? The molecules of water are packed tightest at 4 degrees Celsius. So that's what the temperature of the bottom of the lake is going to be. Okay? Now, that's even if there's a sheet of ice on the top of the lake and you drill a hole and you drop your thermometer 4 degrees Celsius at the bottom. This is a great property. Because if ice was more dense than liquid water, you'd have a huge problem. No life could have evolved in aquatic systems. No life would exist on this planet because ice would form on the surface like it's done for billions of years. And that ice would then sink all the way to the bottom, crushing all the organisms underneath it, and life would not exist in any aquatic form. And we know, and we'll talk about this from evolutionary point of view, we know that nearly all evidence of life on this planet comes from life evolving in water first. So if you take the scientific evidence and life evolved in water first, then ice formation is by far the most important property, because we wouldn't have life on the planet otherwise. Okay? And then one of the other ones that is really nice, and a nice feature, and allows for the water cycle to continue, and so you don't have these stored water molecules that never get back into circulation. We get areas of land that will get rainfall, will have water on them, and be part of the water cycle. Okay? Majority of areas do, is because of the vaporation of water molecules. Okay? So water has this ability to evaporate, go into a gas form, right, and then condense and be deposited through rain, snow, sleet, whatever, at a different area. So we get evaporation coming off of our oceans, we get transpiration coming off of our forests and grasslands and plant material. All of that will condense, and water will precipitate out in some kind of form over the land, and also over the oceans, etc., but over the land, and that just continues that cycle. Okay? The other part of that cycle is even humans and other mammals and other organisms that have the ability to respire and have the ability to sweat. This water will vaporize. Okay? Remember, nothing on our planet is really, nothing at all is created or destroyed. Okay? Now, I know the first law of thermodynamics, maybe we haven't talked about it yet, is that energy is not created nor destroyed. Okay? For that matter, nothing really is created or destroyed. It just changes form. So, you're sweating. That water is not going anywhere except for as a vapor. Okay? It will eventually condense and fall back to the planet. Maybe not where you're at. Maybe if you're in the Sahara Desert, it will take years and years and years and years and years before any water molecule would ever evaporate and transpire back onto, or precip out back onto the area where you're sweating. Okay? But that water molecule is not going anywhere. It will eventually be deposited back on the planet in liquid form. And for that matter, it will eventually be bound up in solid form. So like I said before, every water molecule on the planet today is every water molecule on the planet 4.6 billion years ago. Vaporization is really important for that, that cycle to occur on the planet. So here, just to reiterate that, we're talking about that density, okay, before the ice formation density. Here you can see liquid water. You can see that the water molecules are closer together in liquid water. They're not forming stable hydrogen bonds with each other. Okay, they might form a hydrogen bond for a little bit and then break free, a little bit, break free. Okay, they are still attracted to each other, and that's what holds them close to each other. But in the case of ice, the water molecule bonds are solid. They form stable hydrogen bonds, but the bond length is larger than it is in the case of liquid water. So you have these open spaces. So the density here is less than the density here. That makes ice able to float on water, liquid water. All right, some other properties that are unique to hydrogen bonds or to water. Okay? Cohesion, or the attraction of water molecules to other water molecules. That's how we get raindrops. That's how we get droplets like this. Is that process of cohesion. That's how we get water tension. That's how we get a lot of things that occur with water molecules attracting to other water molecules. Okay, so surface tension like this here. You can see a water strider here. They live their entire life on the surface of the water. That tension, or that ability to walk on this water and live on this water, has to do with the attraction of water molecules to other water molecules. Okay. The other one is the attraction of water molecules to other polar molecules, or what we call adhesion. And so this is a process that drives a lot of things. It drives the ability for water to be what we call the universal solvent. Okay, so it is going to dissolve nearly every polar molecule. It will eventually dissolve. Okay, it is this universal liquid that you can absorb material into. Okay, and it can transfer that material to different places. Okay, that's another really important feature of water. If we are talking about nutrients, if we're talking about, different chemicals that are moving through the landscape, maybe moving from a terrestrial landscape to an aquatic landscape, okay, or vice versa. Water has that ability to absorb those materials, dissolve those materials, and transfer them from one area to another area. And that's adhesion. The other, important feature of adhesion is the ability for things like plants to live. Right? So if you think about something like a redwood tree, redwoods are the tallest, largest trees on the planet. Right? And so if you go to the redwood forest in Northern California, they're spectacular. I mean, they're amazing. You can drive a car through trees because they're so big. Okay? But we're not talking about just the width of the tree or the girth of the tree, but we're talking about the height of the tree. We're talking about trees that are 300, 350, 400 feet tall. That 400-foot tree is still using capillary action to get water from the roots all the way up 400 feet into the canopy. It's pretty amazing that they don't need a heart. They don't need a pump to pump water from the roots 400 feet up to the top of the tree. Instead, they use capillary action, adhesion, so the attraction of water molecules to other molecules. They use, xylem and phloem, okay, which are two tubes. One's for nutrients and one's for water, but they're two tubes that, allow for water to use capillary action and cohesion. These two are working together because water is attracted to water molecules, but it's also attracted to other polar molecules. And it's through that action that water can climb up 400 feet into the canopy of these trees. Okay? It's pretty amazing stuff. So water is highly polar. We talked about this before. One of the other unique possibilities with water is that when water is in solution and it's coming in contact with other polar molecules, it will form the maximum number of hydrogen bonds possible. That's what makes water and hydrogen bonds strong, or molecules that are associated with hydrogen bonds strong, is because hydrogen bonds are at the absolute maximum number. You put something in solution, it's going to form the maximum number of hydrogen bonds. Okay? This makes that material stronger. Okay? That molecule, that composition stronger. That macromolecule or large molecule stronger. There are two kind of properties. You probably heard about these properties before. Hydrophilic molecules or hydro water loving molecules. They form polar bonds with water molecules readily. So they dissolve in water readily. They're attracted to water when they're in solution. Those are hydrophilic molecules, water loving molecules. Hydrophobic molecules are nonpolar molecules. So they're not going to form hydrogen bonds. They repel water. They don't like water. And they don't react with water. They don't dissolve in water. Okay. We'll come back to these. We'll come back to hydrophilic and hydrophobic. But I know you're thinking about things that can't dissolve in water. And you're thinking, well, I know some hydrophobic molecules. Good. That's a good thought process to start thinking about what is hydrophobic. What can you not dissolve in water? Okay? What is hydrophilic? What can you dissolve in water? if you're thinking about that, then you know if it can dissolve in water, it's a polar molecule, or at least when it comes in contact with water, it becomes a polar molecule. The opposite. If it comes in contact with water and it doesn't dissolve in water, then you know it's a nonpolar molecule. And it's hydrophobic. It does not dissolve in water. We'll come back and we'll look at some examples of this, because you can make hydrophobic molecules hydrophilic. Sometimes it just takes adding something to a hydrophobic molecule to allow it to become polar. Sometimes it takes breaking a bond to make that hydrophobic molecule become hydrophilic. Okay, we'll come back and look at these at a later date. Till next time.